previous first session we discussed about the basics of shear force and bending moment, and definitions of bending moment and shear force, and how to draw the bending moment and shear force for the different types of beams. In second session I have solved the problems related to the cantilever beam carrying a point load as well as uniformly distributed load, and also a combination of uniformly distributed load and point load. In this session we will solve the problems related to the simply supported beam carrying in point loads. First, as we discussed previous session, shear force diagram is the diagram which shows the variation of shear force along the length of the beam, and bending moment diagram is the diagram which shows the variation of bending moment along the length of the beam. And also we assume the sign conventions for assume the sign convention: downward forces as an positive, upward forces, that is upward forces means reactions, is negative. Upward, here in this simply supported beam we have to calculate the reactions at the supports. Okay, that's support reactions we are considering as an negative. Then bending moment calculation, clockwise movement we are considering as an negative, anti-clockwise movement we are considering as a positive. Let us take the one simple example where to find out the support reactions for simply supported beam. This is the simply supported beam which carries an central point load. Central point load means it is a L by 2 distance from the support. From the support it is L by 2. When load is acting at center, then to calculate the support reactions we can, because it is symmetrical loading, we can divide that load by 2, that is the reaction at A and B. That means whatever the load of downward force is acting, that must be equal to the upward forces. Here upward force is A is the support A and support B, downward force is W. Reaction at A and reaction B, what we can call it as an RA and RB, is W by 2. This is the RB, W by 2, RA, W by 2. Like this, if symmetrical loading is given, we can calculate the reactions by whatever the downward forces divided by 2. Then we will get the reactions at the RA and RB. If it is in load is not symmetrical, then we have to take the moment about the A or B, because whatever moment at A and B is 0, all the forces acting, that has to be taken into the one point A towards A or towards B, then we can find out the reaction at A and B. This is the case where we have taken the magnitude of 10 kilonewton which is acting at center. When it is acting at center, reactions will be half of the load. Therefore, RB will be equal to 5 kilonewton, that is 10 divided by 2. RA is equal to 5 kilonewton. Whatever the total load, downward force, that is equal to the upward force. We can see here upward force is 5 kilonewton acting. Here one more 5 kilonewton is acting, that is support reactions. If we add these two, that should be equal to the 10 kilonewton. In any case, whatever the downward forces are acting, whether it is a simply support, this is whether it is a point load or uniformly distributed load, we have to we have to calculate the reaction such a way that whatever the upward forces, that is support reactions, should be equal to the downward forces. That is the concept. Now in this case it is a beam with 10 kilonewton acting at an 2 meter from the left support, that is A. In this type of situation the reaction at A and B is not equal, it may be different. To calculate this reaction we have to take a moment about A or B and equal to 0, then we will get the one parameter RA or RB, and then another next equilibrium condition we have to apply: sigma upward forces is equal to downward forces, vertical forces is equal to 0 and sigma m is equal to 0. These are the two equilibrium conditions we are using to find out the RA and RB. Taking moment about A. First I am using a sigma MA is equal to 0, one equilibrium condition, that is MA is equal to 0. This is the, here B is the RB, this portion we are having an RB reaction. This RB reaction is vertical, and this moment towards the A is RB into 6. RB into 6 must be equal to 10 into 2. RB into 6 is the anti-clockwise movement. This is the clockwise movement. 10 into 2 is the clockwise movement. We are taking movement about A. RB into distance is 6 meter. Force into distance is the moment. RB into 6 minus, why it is minus? Because it is a clockwise movement. This is plus. RB into 6 is plus because it is a anti-clockwise movement. 10 into 2 is the clockwise movement, that is negative. RB into 6 minus 10 into 2 must be equal to 0. If we transfer this 10 into 2 to right hand side, then RB into 6 is equal to 20. Therefore, RB is equal to 20 divided by 6, that is 3.34 is the reaction at B. To find the reaction at A, what we have to do? We have to use another equilibrium condition, that is sigma vertical forces must be equal to 0. Here what are the vertical forces acting? RA is the one vertical force, and then RB is the one more vertical force. RA plus RB, these two upward direction force must be equal to 10 kilonewton downward force. That is the condition for equilibrium. RA plus RB must be equal to 10 kilonewton. Now already we have the RB value. That RB value, if we substitute here, we will get the RA as 6.66. That is RA is equal to 10 minus RB value. RB value we have already calculated 3.34. Therefore, value of RA is 6.64. Like this, we have to calculate the reactions first before drawing the bending moment and shear force diagram. If it is in any type of load, whether it is a point load or uniformly distributed load, all the loads has to be taken into the consideration for calculating the reaction. Next, this is the RA value 6.66 kilonewton. RB is 3.34 kilonewton, which is vertically upward direction acting. Okay, now we have the reactions at A and B, and also one downward force acting 10 kilonewton. To calculate the shear force, we need reactions at A and B. Whenever the simply supported beam is given, you should be careful. We have to calculate first reactions. Without reactions, you should not calculate the shear force and bending moment values. Here, let us see, this is the RB 3.34 and RA 6.66 kilonewton. Shear force at B, this B point, RB is acting. No other vertical load is there, only vertical upward direction RB is there, that we have to taken into account. Here minus 3.34 kilonewton is acting at this point. Why it is minus? Upward force is considered as a negative, downward force is as a positive. Therefore, shear force at B is equal to minus 3.34 kilonewton. Shear force at C, already we have the minus 3.34 plus one vertical load 10 kilonewton is acting. We have to add to the 3.34 kilonewton. Therefore, minus 3.34 kilonewton plus 10 kilonewton, it becomes an plus 6.64. Here we can observe shear force at B was minus value and it changes to plus value at the C. Shear force at A is no further load is added in between the A to C. If any other load is added, then we have to add to this previous value of shear force. Now no further load is added, therefore shear force at A is equal to 6.66 kilonewton. 3 points, whatever the A point and B point as well as point load where it is acting, 3 points we are calculated the shear force. For calculating bending moment at B and bending moment at A is 0 for simply supported beam. Bending moment at B is equal to 0. Because it is freely supported, there is no moment. Bending moment at C. To calculate bending moment at C, first we have to consider RB. RB into distance. It is anti-clockwise. RB into distance. What is the distance? Total is 6 meter minus 2 meter. Balance from C to B is, C to B distance is 4 meter. RB into 4. Only one force is acting, that is upward direction. RB into 4. That is the moment at C. 13.36 kilonewton meter at C. Now we have the values. Bending moment at B is 0 as well as bending moment at A is equal to 0. Central value 13.36. Similarly, we have the three values of shear force: 3.34, 6.66, 6.66. Let us draw the shear force and bending moment diagram. This is the beam given. First draw horizontal line. Now what is the value of shear force at B? 3.34. It is negative, that is why we have drawn the line downward. 3.34 kilonewton. Then from B to C it is constant. At C it is suddenly changes to 6.66. But you should see 6.66 plus 3.34, total should be 10. This total drop should be equal to 10 kilonewton. Previous session also I explained, wherever the shear force is, wherever the point load is acting, that particular place, the vertical drop should be equal to the load. Here 6.66 plus 3.34 is equal to 10 kilonewton. Okay, then from here C to A it is constant. Then 6.66, close the polygon. This is the shear force diagram where plus positive left side and negative at right side. One particular point where shear force changes its sign. It is become a negative to positive. This point we will get the maximum bending moment. Maximum bending moment. Where shear force changes its sign, that particular point we will get the maximum bending moment. Okay, let us see whether we are getting a maximum bending moment at this point. We can observe at A it is 0, B it is 0, then only one point load is there, that place we are having a maximum bending moment. For drawing the bending moment diagram, first draw the horizontal line and then 2 points, it is 0 A and B it is 0. Then mark central this point below the C mark the point where it is 13.36. Then join the starting point to the central point, this C point. Okay, we can observe here 13.36 is maximum bending moment at where shear force changes its sign. This is plus value. Okay, this is a sagging bending moment. This is the bending moment diagram which is having a triangle shape, and here two rectangles are there for shear force diagram. One particular point where this shear force changes its sign, that place we will get the maximum bending moment. Let us consider one more problem where we are having one 10 kilonewton is acting at a distance of 2 meter, another load is acting at a distance of 2 meter from B, one load is acting at a distance of 2 meter from A, and one more is 2 meter from B. And what I have written here, this is the moment, this is in this direction, this is clockwise movement, this will also develop in clockwise movement, this will develop the anti-clockwise movement. Therefore, these two movements, these load, whatever the moment we are taking from 10 kilonewton, these two loads 10 kilonewton and 10 kilonewton, it should be clockwise movement and support reaction is anti-clockwise movement. First we have to calculate the support reactions. For calculating the support reactions, we have to take the moment about A. MA is equal to moment about A is equal to 0. First reaction RB, that is anti-clockwise movement, RB into 6, RB into distance from A to B is 6 minus, because it is in this direction, minus 10 into distance is 10 into distance from this point to A point, that is 6 minus 2, that is 4 meter. 10 into 4. Next one is again clockwise movement, 10 kilonewton acting downward, that is 10 into 2, distance is 2 meter. 10 into 2, 10 into 4, and then RB into 6. These two we are considering as a minus value, and RB into 6 is positive moment, equal to 0. Then we will get RB into 6 is equal to 60. Therefore, RB is equal to 60 divided by 6. We got the value of RB. RB value. To calculate RA, second equilibrium condition, that is sigma vertical forces is equal to 0. Of the 10 kilonewton, 20 kilonewton is acting downward, and then RA and RB are the upward forces. RA plus RB is equal to 10 plus 10, 20 kilonewton. RA plus RB is equal to 20 kilonewton. RA is equal to 20 minus RB. Therefore, 20 minus 10 is equal to 10 kilonewton. Here we got the RA value and RB value as a 10 kilonewton. Why we got the equal values? You can observe here. From A, 10 kilonewton is acting at a distance of 2 meter. Similarly, from B, it is acting 10 kilonewton at a distance of 2 meter. Both the loads are symmetrically loaded at an equal distance from the A and B. That is why when load is symmetrical, then reaction will be equal. 10 plus 10, 20 divided by 2, 10 kilonewton RA, 10 kilonewton RB. If it is not symmetrical, then reactions will be different. Now let us draw the shear force and bending moment diagram. Shear force at B point, it is 10 kilonewton vertically upward direction, okay, minus 10. Why it is minus 10? Because it is the upward direction. Then shear force at C point, whatever the previous value 10 kilonewton plus one more point load is added, 10 plus 10, minus 10 plus 10, plus 10 is downward and upward is minus 10. Therefore, shear force at C becomes a 0. Shear force at D, previous value 0 plus 10 kilonewton is acting downward plus 10. Therefore, shear force at D is equal to 10. From D to A, no load is added. D to A, no load. Therefore, shear force at A equal to whatever the 10 kilonewton previous value is there. Therefore, shear force is constant from D to A. Shear force is constant from B to C. From C to D, shear force is 0. Next, bending moment. Bending moment at B is equal to 0. For simply supported beam, bending moment at supports is 0. Bending moment at C point, force is RB, force is RB into distance is 2 meter. We are taking the moment about C, RB into 2, 10 into 2, that is 20 kilonewton meter at C. Bending moment at D this point, how to calculate this RB into distance from D to B. D to B is 10 into 4. 10 into 4. 4 is the distance from D to B minus, because it is a 10 kilonewton, this is the clockwise movement, 10 kilonewton into distance from C to D. Total distance is 6 meter minus 2 meter, minus 2 meter. Two sides 2 meter is there. If we minus from 6 meter, we will get the distance between the D to C is 2 meter. Therefore, 10 into distance is 2 meter. 10 into 2. 10 into 4 is the first is 10 into 4 is the RB into distance from D. 10 into 4. Then another load is 10 into 2. That will be 20 kilonewton meter at bending moment at D. Or we can calculate the bending moment at D by from left side, that is RA into distance. RA into distance means 10 into 2, 20. We can calculate the bending moment from right side or left side. Bending moment at A point, it is 0. Bending moment B is 0, bending moment A is also 0. Now we have the values of shear force and bending moment at salient points A, D, C, B. Let us draw the shear force diagram. First draw horizontal line, then here downward, that is equal to RB value. Shear force at B will be equal to RB value, 10 kilonewton. Then it is constant from B to C, 10 kilonewton. At C it becomes 0. Again at D 10 kilonewton and it remains constant. This is the shear force diagram. What we can observe, shear force is 0 from D to C, and then at support it is 10 kilonewton, left support also 10 kilonewton, right support also 10 kilonewton. This is the shear force diagram. To draw the bending moment diagram, first draw the horizontal line, then mark the points at D point and C point, values of bending moment. These are the two values, 20 kilonewton, 20 kilonewton meter, 20 kilonewton meter, 20 kilonewton meter. Next draw straight line, inclined line from B point to C point, and then from C to D bending moment is constant, then D to A, D 20 kilonewton meter, then it becomes a 0. This is the diagram for bending moment. What we can observe here, this is the constant, bending moment is constant from the C to D. Now let us consider 3 point loads. Previous problem we considered the 2 point loads. Here 3 point loads are acting on the beam. From A support, left support, it is 1.5 meter, 20 kilonewton acting. From the left support, 3.5 meter distance, 40 kilonewton is acting, and one more load is acting 60 kilonewton at a distance of 1 meter from the right support. We consider the 3 point loads, and it is not symmetrical. It is not symmetrical loading, you can observe, because this load is not acting at the center, and this is also not exactly 1 meter what is given right side. Therefore it is not symmetrically loaded. That is why we have to calculate the reactions at RA and RB by taking the moment. Taking moment about A, MA is equal to 0. Now just observe, RB is the value we needed. RB into distance is 6.5 meter. This is anti-clockwise, positive, and balance all other moments are negative. That is why all the negative moments we are taken into the right side, transferred to the right side. If we write here minus 60 into 5, instead of that one I have transferred to the right hand side. 60 into this is clockwise movement, 60 into distance from A, C to A. Total distance is 6.5 minus 1 meter, 5.5. 5.5 is the distance. 5.5 into 60. 60 into 5.5. Next load is 40 kilonewton. 40 into 3.5. 40 into 3.5. Then 20 kilonewton. 20 into distance is 1.5. 1.5. 60 into 5.5 plus 40 into 5.5 plus 20 into 1.5. This is the total moment of loads, and RB into 6.5 is the moment due to reaction. From this we can easily calculate the RB is equal to 76.92. We have the value at value of RB. To calculate RA, what we have to do? We have to use the equilibrium condition. Sigma V is equal to 0. Vertical forces, what are the vertical forces acting? 40 kilonewton, 60 kilonewton, 20 kilonewton. 60 plus 40 plus 20, 120. Downward forces 120 is acting. Upward force we have already RB is equal to 76.92. Back taking moment about A, RB into 6.5. RB is anti-clockwise. RB into 6.5 is equal to, this is the anti-clockwise, I have taken left hand side, and clockwise moment to the right hand side. If instead of writing in minus this 60 into distance, instead of writing in 60 into 5.5 minus, I have transferred to the right hand side. Now this is RB into 6.5 is equal to 60 into distance from A to C. What is the distance from A to C? 6.5 minus 1. 6.5 minus 1 is 5.5. 60 into 5.5. Next load is 40. 40 into distance is 3.5. 20 into 1.5. 20 into 1.5. All these are all the negative. That is all the negative moments are transferred into the right hand side, and left hand side reaction, this moment due to reaction. RB into 6.5 is the moment due to reaction, and all other moments are due to the load. If we equate this, we will easily get the RB value. RB is equal to 76.92 kilonewton. Now next we have to find out the RA. To calculate the RA, what we have to do? Add the forces. Upward forces must equal to the downward forces. Upward force is RA and RB. Reaction at A and reaction B. Downward force is 60 kilonewton plus 40 kilonewton plus 20 kilonewton. 60 plus 40 plus 20, 120 kilonewton. 120 kilonewton should be equal to RA plus RB. RB already we have 76.92. Therefore RA is equal to 120 minus 76.92. See, 120 is the load, total downward load, and total upward load is RA plus RB. RA is equal to 120 minus RB. Therefore 43.08 kilonewton is the reaction at A. Reaction at A is equal to 43.08, reaction at B is equal to 76.92. When any type of loading is given for simply supported beam, first you should carefully calculate the reactions. For calculating the reactions, first you have to take the moment about any one point, about the reaction A point or B point. After calculating one reaction RA or RB, then another reaction we have to calculate by using the equilibrium condition, sum of the upward forces is equal to sum of the downward forces. Next, after having in reactions at A and B, we can easily calculate the shear force and bending moment values. Shear force at B, always shear force at support will be equal to the reaction. Reaction is 76.92. It is minus value because it is a upward force. Reaction at C, to calculate shear force at C, to calculate shear force at C, minus 76.92 is the value at B, plus 1 point load is added 60. That will be equal to 16.92. Next, shear force at D, previous value is 16.92 plus one more load is added 40 kilonewton, that will be equal to 23.08. Why we are taking in plus? Downward force we are considering positive and upward as a negative. Next, shear force at E, previous value 23.08 plus 23.08, for that plus 20 kilonewton, that is equal to 43.08. From E to A, no load is there, therefore shear force at A is equal to 43.08. You can see here one particular point, you can observe one particular point, shear force is changed, its sign. Here minus 16.92 at C, whereas at D it is plus 23.08. From C to D there is a change of shear force, minus to plus. Next, when we are drawing the shear force diagram, we will discuss this. Next is to calculate the bending moment values. Bending moment at B is 0 for simply supported beam. Bending moment at the support is 0. Bending moment at C point, from the right side of the C, we have to see only right side of the C. Right side of the C only one force is acting, that is reaction, RB. 76.92 into distance is 1 meter. RB into distance, 76.92 kilonewton meter is the bending moment at C. Next, bending moment at D point, you have to see right side of the D, or you can calculate from the left side of the D. See, right side of the D, what are the forces acting? One is RB and another one is 60 kilonewton. First, take the moment of RB. RB is moment is anti-clockwise, that is why we will consider as in positive, and moment due to C is clockwise, that is why we will consider as a negative. See what 76.92 into distance is from B to D. 6.5 is the total distance, minus 3.5, that is 3 meter. 3 meter is the distance from B to D. 76.92 into 3 minus, this is positive because anti-clockwise, and then minus 60 is the load, 60 kilonewton into distance from C to D. What is the C to D distance? C to D distance is, total distance is 6.5 minus 3.5, that is 3 meter. 3 minus 1, that is 2 meter from distance between the C to D. 60 into 2, 76.92 into 3 minus 60 into 2, we will get the bending moment at D, 110.76 kilonewton meter. Next, bending moment at E. Bending moment at E, you have to take the moment of all the forces right side of the E, or you can take the moment of all the forces left side of the E. First, we will take from the right side. See, RB is 76.92 into distance between B to E. B to E distance is 6.5 minus 1.5. 6.5 minus 1.5 is 5 meter. 76.92 into 5. This is anti-clockwise. Then 60 kilonewton into, this is clockwise, 60 kilonewton into distance from C to E. C to E is total distance is 6.5 minus 1 meter, that is 5.5 minus 1.5, 4 meter. 4 meter into 60, that is distance from the E to C is 4 meter. Next 40 kilonewton into distance from E to D. E to D. E to D distance is, we are taking moment about E, that is why we need the distance between the E to D. That distance is 3.5 minus 1.5. 3.5 minus 1.5 is 2 meter. 40 into 2, that's all. 40 into 2 is the one load, 60 into distance 4 meter, and then RB into 5 meter. These are the three forces acting right side of the E. Therefore, calculate this, we will get the 64.6 as a bending moment at E. Bending moment at A is equal to 0. Or we can calculate the bending moment at E. Bending moment at E by calculating the RA into distance. RA is 43.08 into 1.5. That will you will get 64.6 itself. RA into 1.5. That is left. If you take from left side or right side, we have to consider three forces. Left side only one force. We will get same value 65.6 kilonewton meter. These are the bending moment values. Let us draw shear force diagram first. Here 76.92 is the value at B, that is equal to RB, constant up to C, then it is 16.92 at C, again constant up to D, then it is changes to 23.08 at D, again it is constant up to E, again it changes to 43.08, again it is constant, finally close. What you can observe here, see this is the point where 23 point, you can observe here wherever the point loads are there, there is drop. That drop must be equal to the value 76.92 minus 16.92, it is the 60 drop here. Okay, then 23.08 plus 16.92, 40 drop here. From 43.08 minus 23.08, 20 drop. This vertical drop should be equal to the point loads value, and at support it is reaction value. Here 43.08 is the RA value, 76.92 is the RB value. And one more important point here, change, shear force changes its sign. That is why that place we will get the maximum bending moment. Bending moment will be maximum at D. Let us see whether we will get the maximum bending moment at D or E or C. This is the shear force diagram. For drawing the bending moment diagram, first draw the horizontal line, then mark the salient points below the each point. E point, project the E point and mark the 64.6, project the D point, mark 110.76, project the C point, mark 76.92. This should be proportionate scale. You have to be draw the diagram proportionate to the values. Then join all the points. You can observe here maximum bending moment 110.76. Then bending moment gradually reduces 64.6 and 0. Right side also it is 76.920. That means wherever the shear force changes its sign, that place we will get the maximum bending moment. This is the bending moment diagram. Next consider the uniformly distributed load. We have solved problems related to the point load. Let us take the uniformly distributed load. This is the simply supported beam AB carrying an uniformly distributed load throughout its length 5 kilonewton per meter. Okay. For this beam we will take one more point, C point, midpoint A, B and C. For this we can calculate the maximum bending moment, maximum shear force easily. What I have given the cases in first session. Maximum bending moment will be is equal to WL square by 8 and shear force, maximum shear force is WL by 2 and maximum bending moment occurs at the center. But we will solve this problem step by step. This is the load 5 kilonewton per meter. It is acting throughout its length. That means it is completely it is loaded. To calculate the reactions RA and RB, whatever the load divided by 2, because load is acting throughout its length 5 kilonewton per meter. It is 6 meter. 5 into 6 is the 30 kilonewton. Total load is 30 kilonewton. I explained in the first session and second session how to convert the uniformly distributed into the equivalent point load. Whatever the load is there into distance, if you multiply, we will get the total load, and it acts at the center of its length. That is 6 meter is the length, it acts at the 3 meter distance. Now 5 into 6 is the 30 kilonewton, that is the total downward load, divided by 2 is 15 kilonewton at A and 15 kilonewton at B. This is the reaction at RA and RB. To calculate this, we can take moment and let us verify whether we will get the 15 kilonewton. Take the moment, taking moment about A, that is RB into 6. RB into 6 is the distance is equal to 5 into 6 is the load into it is acting at a distance of 3 meter. 6 divided by 2, that is equal to 90. This is the RB into 6 is the anti-clockwise and this load moment is the clockwise. That is why we are equated clockwise moment is equal to anti-clockwise moment. RB into 6 is equal to 5 into 6 into 6 by 2, that is 90. Therefore RB is equal to 15 kilonewton. Now RA plus RB must be equal to the 5 into 6, that is 30 kilonewton. RA plus RB is equal to total load 30 kilonewton. RA is equal to 30 minus RB, that is 15 kilonewton RA. Like this we can calculate by taking the moment. Since it is loaded completely, we can easily calculate without taking the moment. 5 into 6, 30 kilonewton divided by 2, 15 kilonewton RA, 15 kilonewton RB. To calculate the shear force, as I explained, shear force at B equal to RB value minus 15 kilonewton. Shear force at C minus 15 previous value plus from C, right side of the C, whatever the load is acting, right side of the C we have to consider. Right side of the C is half of the load, that is 5 kilonewton per meter for a distance of 3 meter. 5 into 3, 15 kilonewton. We have to consider half load only. 5 into 3 is the 15 minus 15 kilonewton plus because it is downward and minus 15 kilonewton previous value, that will be equal to 0. Shear force at C is equal to 0. Shear force at A from C to A, from to C is to A is 0 plus previous value 0 plus 5 kilonewton per meter for distance of 3 meter it is acting. 5 into 3 is equal to 15 kilonewton. Okay, this is the shear force value. Now calculate bending moment at B. Bending moment at B is equal to 0. Bending moment at C, right side of the C we have to consider. Right side of the C is 15 into 15 kilonewton RB into distance 3 meter. From C to B is distance is 3 meter. This is anti-clockwise, that is why considered as n plus. And then this load is acting clockwise. 5 into 3 is the load and this 5 into 3 is acts at the center of 3 meter. That center point is 3 by 2. 5 into 3 into 3 by 2. Then we will get the 22.5 kilonewton per meter is the bending moment at C. Bending moment at A is equal to 0. Both support it is 0. Let us draw the shear force diagram. Shear force diagram, first draw the horizontal line, then 15 kilonewton downward, 15 kilonewton here plus, here minus. This is RA value left side, RB value right side. Then at C point it is a 0. Then join from A to B, C point it is 0. What we did here, because it is a uniformly distributed load, this shear force diagram will be sloping. Where uniformly distributed load is acting, that portion we have to draw the sloping line. This is the point where we are getting a maximum bending moment. First, for drawing the bending moment diagram, draw horizontal line, then mark the center point C point, its value, and then join by the parabolic line. We have to draw the parabolic line for the uniformly distributed load. 22.5 is the maximum bending moment which is at the center. This is for the case for simply supported beam carrying an uniformly distributed load throughout its length. Let us consider one more example where uniformly distributed load is acting left half of the portion. This is not loaded fully, therefore reaction will not be equal, and also you can observe obviously reaction at A will be more because load is acting towards A. Here B may be less, taking moment about A. Now you can say RB into 6 is the distance, RB into 6, this is anti-clockwise movement, must be equal to the clockwise movement. 5 into 3 is the load, 5 kilonewton per meter into distance is 3 meter, 5 into 3 into it is acting at a distance of half of 3 meter, 3 divided by 2, mid of this 3 meter, 3 divided by 2, 5 into 3 load into distance is 3 by 2, that is equal to 22.5 kilonewton meter. Therefore, RB is equal to 3.75. To calculate RA, upward forces RA plus RB, downward force is 5 kilonewton per meter into 3. That is total downward force acting is 5 into 3, 15 kilonewton acting. 5 into 3 is the 15 kilonewton, because when UDL is given, we have to convert into the point load by 5 into 3. Therefore, RA is equal to 15 minus RB, that is 11.25 kilonewton. We have the values of RA and RB. You can observe here RA value is more, RB value is less. Since load is acting towards the A, that is why RA value is more. RA RB values are not equal. It is not symmetrically loaded. Let us calculate the shear force. Shear force at B minus RB value. RB value is 3.75 kilonewton. Shear force at C constant. No load is added in between the C to B. That is why it is constant 3.75 kilonewton. Shear force at A minus 3.75 is the previous value, plus load is 5 into 3. Total load acting from A to B is 5 into 3, 15 kilonewton. Therefore, shear force at A is equal to 11.25. See, you can observe RA also 11.25. Shear force at A will be RA value, shear force at B will be RB value. In between that, we have to calculate. Next, bending moment at B is equal to 0. B it is 0. bending moment at C, RB value into distance. RB value into distance between here to here is C to B is 3 meter. 3.75 into 3, 11.25 kilonewton meter. Bending moment at A, 0. Bending moment at C is 11.25. Bending moment at A is equal to 0. A and B are 0 and C we have calculated by taking moment of RB value, because RB only one load is acting right of the C. Let us draw the shear force diagram. See here RB value we have drawn 3.75, then left side RA value 11.25, it is positive, right side it is negative, and it is constant up to C. Then it should be inclined line. We have to draw in the inclined line, because where uniformly distributed load is acting, that portion it should be inclined line. Okay, this is the point somewhere bending moment is maximum. That point we will calculate next session. Okay, then to draw the bending moment diagram, you mark the point C point 11.25 and 0 at the A and 0 at the B. We have to join by the inclined line up to the C, and then from C to A point it should be parabolic line. It should be parabolic, because where UDL is there, that portion we have to draw the parabolic line, and this is the point where we will get the maximum bending moment. That maximum bending moment in next session we will take up. And next one more example I have taken. Here you can see uniformly distributed load is acting right side. We can take the moment about A, RB into 6 distance is equal to 5 into 3 is the distance, load acting, 5 into 3 is the load acting, and it acts at the center of this 3 meter. Center of 3 meter, that is 3 divided by 2, plus distance from A to this point, center point is 3 plus 3 by 2. 3 plus 3 by 2 is the distance, into 5 into 3 is the load. 5 into 3 into distance from this center point to A, 3 plus 3 by 2, that is 4.5. That is the value 67.5 kilonewton meter. Therefore RB is equal to 11.25. RA plus RB must be equal to the 5 into 3, that is 5 into 3 is the load. 3 is the distance, up to 3 meter it is acting. Therefore RA is equal to 3.75. Then we can calculate the shear force. Shear force at B is equal to 11.25 RB value. Shear force at C is equal to this RB value previous value minus 15. How we got the 15? 5 into 3 is the value of a load. Then shear force at A is 3.75, that is RA value. Then bending moment also we can calculate similar way how we did in the previous problem. That is bending moment at C is 11.25, bending moment at A is 0. Then we can draw the diagram. Here you can see reverse of previous problem. Where UDL is there, that portion is inclined. This is the place where we will get the maximum bending moment, and these are the values of shear force. And you can see the bending moment diagram also. This point, particular point where we will get the maximum bending moment, and 11.25 is the value at the C, and left side it is an inclined line, and right side is a parabolic, because it is a uniformly distributed load is acting. Okay, we will discuss these further problems in the this is the one more example I have taken here. You can see uniformly distributed load is acting at the central part. Central portion is inclined, and all the other portions, left side is RA value and right side is RB value, and exactly center it changes its sign, because it is a symmetrically loaded. Exactly center it changes its sign. This is the bending moment diagram, and this central portion maximum bending moment occurs, that we will discuss in the next session. Left side and right side is inclined line, central portion is the parabolic. These are the cases we are considered: 1 point load, single point load, and 2 point load, 3 point loads, uniformly distributed load throughout its length, uniformly distributed load left half of the portion, uniformly distributed load right half of the portion, and then uniformly distributed load central portion. Okay, these are the different types of problems we discussed today. Next session we will see combination of uniformly distributed load and point load, and for that how to calculate the bending moment and shear force diagram. Thank you.